Up, it's day 81. We started looking at some rate in, rate out problems today in class. I want to do kind of a full example that kind of takes care of all the kind of different questions they might ask or they like to ask on the AP free response section. So go ahead and just pause the video right now and copy this prompt down into your notes. It's really important for you to copy it into your notes right now because we're going to annotate it to make sure that we understand this really well and get everything 100% right. Okay, so now that you have this copied in, I say water fills a tank at a rate of R of t equals that ugly thing, where R of t is measured in liters per hour for 0 to 8 hours. So that's the water filling the tank. What I want you first to do is to annotate what R of t is here. This is rate in. Okay, that's our rate in. Because it says water fills a tank. So that's the rate of water going into a tank. The first thing I want to do right now is go ahead and graph that function on my calculator. And again, I've been telling you guys this in class, but you only need to type this function in once. Just make sure you type it in correctly that one time. So I'm going to my graph screen here. I'm going to clear the junk that's in there. I'm going to go ahead and type in my function, 6 plus 4 sine, and I'll use my fraction bar, x squared over 15. And again, I think everybody knows this by now, but even though the function has a t in the problem, we type it into our graph with x. Okay, so that's our rate in. It said our window was from 0 to 8. So I'm going to go ahead and set that window from 0 to 8. And I know that sine can be between plus and minus 1. So this thing is going to go maybe as high as 10, as low as, I'll just do 0 to 10 for my min and max here. I'll just hit graph to see what this thing looks like. So there we have it. That's our rate in. Okay, let's go back to the problem. Oh, what I want to annotate right now, not only is this the rate in, but this is y1 in my calculator. We notice that R of t is measured in liters per hour because it's a rate, and it goes from 0 to 8 hours. Okay. All right, now it says after 2 hours, a plug is removed from the tank, and the tank drains at a constant rate of 5 liters per hour. So this tank draining at 5 liters per hour, this 5 is our rate out. Now this is just a constant rate of 5. So I'm just going to go ahead and go back to my graph here. And for y2, I'm just going to graph 5. Okay, so there we see our rate out. It's a constant rate. That's my rate out. It's just the function 5, right? It's just a horizontal line of 5. That's our y2. But what's really important here is that I don't start draining the tank until 2 hours after. So this is only between 2 and 8 hours, right? I would annotate that with something to draw your attention to it, because eventually that's going to be very important. We saw that on the banana problem today, right? Paying attention to rates not starting until a little bit later than the other one starts. Okay, So we got our rate in as Y1, we got our rate out as Y2. The last thing that's very important here, it says at t equals 0, the tank has 60 liters of water in it. Okay. What is that? That's our initial condition. Now, some of the questions I'll ask you about, the initial condition won't really matter. Some of the questions I ask you about, the initial condition really matters. And I want you to get used to reading these to know when is that initial condition going to matter and when won't it. Okay? But we want to note it in there. Even if we don't use it in part A, we might need it in like part C or D or something, and we want to have it labeled so we can find it quickly. Right? Because this whole thing is we're on a clock, so we want to be as fast and efficient as possible. Okay. So my first question is, okay, so the first question is, how much water was added to the tank in the first 4 hours? They might say something like, how much water in liters was added to the tank in the first 4 hours. Okay. Now, does water added to the tank relate to our rate in equation or our rate out equation? Well, clearly that relates to our rate in equation. And I know the rate in, but I want the amount in, so I have to integrate the rate in. Okay? And I want it in the first 4 hours. And notice that that rate in, that does start at 0, at t equals 0, right up here. The rate in does start at 0, so I don't have to, I'm not going to get, there's nothing to be tricked by here. This is simply, the answer to this question is simply the integral from 0 to 4 of our rate in. Now, here's where it's nice. Since I already entered RT into my calculator, and I have a little reminder up here that that's my Y1, I have a reminder up here that that's my rate in, I know that I can just go to my calculator now. And I can do math 9, integral 0 to 4 of alpha trace. Alpha trace is where we get our y variables from. And I want to do y1 because that was the one that associated with r. And I get 29.243. Okay, so that's the number of liters of water added in the first 4 hours. Okay. Pretty simple problem, as long as we remember that integrating the rate in will give us the total amount added. Now ask yourself, did we care about the initial condition here? Well, the answer is definitely no. I couldn't care less about the initial condition, because no matter how much water was in there, that doesn't matter to begin with. This is how much simply I added to the tank. Okay? I didn't need to care about my initial condition there. Next question. Okay, so here's the next question. It says, find r prime of 3, and then using correct units, interpret the meaning of r prime of 3 in the context of the problem. I think part 1 of the question here is very simple. Part 2 is a lot more difficult for most people. Okay, so I'm finding r prime of 3. So that means I'm doing the derivative of r evaluated at a time of 3. Right? To do your derivative, you can do this. I'm going to show you 2 different ways to do this. The way I usually do r prime of 3 is through the graph. So I'll go back to my graph and at second calc, dy dx. Now, since I have 2 functions in here, I have to make sure I'm doing the derivative of the actual function I want. It's supposed to be of r, and r I know is my y1. It always will default start you on y1, so I don't need to change anything here. But if I needed, the derivative of y2, I'd have to hit down on the direction pad to get to the other function. I don't need to do that here. Then I just type the number 3 and hit enter. And it says dy dx equals 1.321. So I'll go back to my deal and I'll say 1.321. Okay? And now we have to start thinking about units. Actually, before I do that, let me show you the other way. If you don't like doing the derivative through the graph screen, go back to your main screen. We know Math 9 is for an integral. Math 8 does a derivative. So just to show you this, we haven't looked at this very much. dx always. And then we want to do the derivative of alpha trace y1 at an x value of 3. And you see I get that same answer of 1.321. So Math 8 works for derivatives, Math 9 works for integrals. Okay, you can see we get the same answer there. Okay, so I know derivatives are always rates of changes, right? So whenever I do a derivative, it's a rate of change, so I have to divide by a time unit. But r of t was already in liters per hour. So the derivative of liters per hour is liters per hour squared. This is a rate of change of a rate of change. So this ends up being liters per hour squared. Okay. Now let's talk about the meaning. Again, this is the rate of change of r. So one thing you can say here is this is the rate of change of the rate of water filling the tank, because that's what r is. It's the rate of change of the rate of water filling the tank at time equals 3. At time equals 3 hours, right? So, and that number is 1.321. So the rate is increasing because of that, because that's a positive answer. So I'm going to show you 2 different ways that you could write this. Okay. But the way I usually see it written on the keys for the scoring guidelines is this. They're going to say the rate of water filling the tank that's referencing to R is increasing. I say increasing because this sign out here is a positive. Is increasing at 1.321 liters per hour squared at t equals 3 hours. So I always want to reference this number here, just like we want to reference the numbers on a definite integral. Okay? The other way you could write this is you could say r prime of 3 is the rate of change of the rate of water filling the tank at t equals 3. So a derivative is a rate of change, but R was already a rate of change. That's why our units there are liters per hour squared. It's a rate of change of a rate of change. Okay, next. Oh no, I'm about to run out of time. Shoot. Okay. Let's do this. Let me state part C, and then I'm gonna have to stop the video. And I'll state part C and D, and I'll let you try those on your own, and I'll fill them in a little bit later. So question C is, at t equals 6, is the amount of water in the tank increasing or decreasing? Justify. Okay. Part D says, what is the maximum amount of water in the tank during the first 8 hours? Okay, so go ahead and solve those, and I'll fill in. I'll do day 81 part 2 here in a little bit, and I'll fill in with the answers. Thanks. Talk to you guys later. To James. Bye.